Hello, everybody. Thank you very much for having me here and to be able to share some of the things that we're doing at VoxelMaps as well. By the way, great presentations from Rob and from Paige. Lots of really interesting things actually to think about, both from some of the technology that we're looking at as well. While we don't directly do subterranean stuff, there could be some interesting applications as well. So let me get started. Let me share my screen. So as Gavin was saying, what I want to talk to everybody about today is this concept of what we call 4D volumetric mapping, and around that creating digital twins, and then leveraging AI to look at how we can extract value from that digital twin. So I know in one of the sessions yesterday, definitely the concept of digital twins came up, and people are starting to hear this terminology in a lot of different industries, not just mapping, starting to be used in a lot of technology sectors that we see. So what I'd like to cover today is to really delve down into what do we mean by volumetric mapping, what is the concept, the technology behind some of those things. Talking then about the digital twins, so how do we actually create a digital twin? What is it to start with? How do you build one? What are the technologies and the approaches used? Then we'll look at AI asset extraction. So how can we apply artificial intelligence and machine learning on the digital twin model to extract features automatically? So can we get the AI to do all of this heavy lifting so there's much less human involvement in that kind of task? And then just finishing up with just a few real world examples of different customers that have been using our technology. So moving on. So what are 4D volumetric maps? So to define this, I just want to spend a few minutes looking at sort of 3D maps. And 3D maps to different people mean different things. Most people will visualize something like this. So this is a screenshot from Apple's 3D maps. And it looks very pretty. It's designed for consumers to use and to interact with as well. But the majority of 3D maps are approximate visualizations of cities. They're not very detailed. In fact, the 3D objects and 3D buildings are empty 3D meshes. So they don't have actually any inherent information inside them. They're just a shell. And so subsequently, they're pretty low accuracy, generalized structures. Again, for visualization, that's absolutely fine. If you want to do something more detailed, then you're going to really start to lose out on information. And you can see this if you just zoom into a lot of these maps, whether this is Apple or Google, they're pretty much the same kind of thing. So you have a 3D object that's been created, and then you've taken an image and you've kind of warped it over, kind of squished it onto the object to create a texture. So it kind of looks similar. But clearly when you're looking at this, there's not a lot of detail. It's not reflective of really the shape of the building. In general terms, yes. In detail, no. So let's contrast that with volumetric mapping. So a volumetric map is a highly accurate measurement of the shape and size of all objects in the environment. So these are very, very detailed maps. You really can zoom in and see tremendous detail in them. In terms of the accuracy, we're talking 1 to 4 centimeters of dimensional accuracy. That means when we're measuring the size of something. And in terms of absolute positioning, we're currently around 8 centimeters in terms of absolute accuracy of where an object is on the planet. In addition to that, the volumetric map has the benefit of adding this fourth dimension of time that Gavin was mentioning here as well. So by looking at this fourth dimension, we can start to apply machine learning, not just to recognize the objects and the assets, but to look at how they've changed over time. And so that becomes a really important dimension as we're starting to collect more and more of this data and building these models. So I want to just touch very quickly on some of the concepts and the theory. Hopefully I won't bore people with this, but I think it's kind of very interesting. So the approach that we take isn't to use points. Points are starting points. If you have a LiDAR and it's creating a point cloud, that's useful input data. But what we do is we use voxels, and clearly the clue is in the name here. So a voxel is just a 3D pixel. Some of you might be familiar with them, others not. Essentially, it's just a cube. And voxels aren't really new technology. They've been used in a number of areas for a period of time now. The first area really to adopt them was computer gaming. So I'm sure some of you might have played Minecraft, or maybe you have children that have played Minecraft. But this is an example of a voxel rendered world, albeit for a game's purpose. Over this year and next year, you'll start to see a lot of gaming engines and new games coming out using voxels, because there's some very nice multi-resolutional capability with voxels. And that becomes kind of advantageous in comparison to some of the things that you can do with polygons. But there's another industry that has been using voxels for quite a while, and that's robotics. And in robotics, you use voxels in one of two ways. First, as an image processing technique to reduce the size of a point cloud. So if you have billions of points, rather than process every single one, you can kind of group them together in voxels, and it makes it easier in terms of the computation time. The other area that is being used is in a form of mapping called VOGs, or voxel occupancy grids. And these are typically used in robotics for kind of small robots, that go into a room, it has a LiDAR sensor, and it builds out a 3D map of the environment that it can localize itself from. And this becomes kind of a small dynamic map, which it stores, for a temporary amount of time and then kind of deletes as it goes into different environments. We took that concept, but we applied it onto a planetary level. So the actual area of research is something called MRVogs, or multi-resolution voxel occupancy grids. So what we did is we took the planet and we placed a giant cube, a megavoxel, over the Earth, as you can see here, virtually, obviously. And this is then comprised of multi-resolutional voxels. Theoretically, they can be any size, so anything we could prescribe to it. But for our purposes, we use 8-meter voxels, which are pretty large, down to 1-centimeter voxels, which are very small. Now, each voxel has a permanent position in space, which doesn't change, and it has a unique address. And so think of it as just an addressing, a 3D referencing addressing system. To start with, there's no information contained in it. It's just a model. So what we then do is we validate what we call the occupancy status of the voxel. Basically, is there something in the voxel or is it free space? So we primarily do that using LiDAR. If we pass a LiDAR sensor through the environment and it's firing its laser beams, if a laser beam passes through a voxel and it's not reflected off anything, then we label this as free space. But if the laser beam hits a surface and collapses down to the smallest unit of the voxel, we label this as occupied. So what we're doing essentially is we're etching out the matter of the planet and creating this very accurate model. Now, one of the things to also bear in mind is that this model goes all the way through the Earth and through buildings. So the same referencing system works outdoors, indoors, and subterranean as well. So it has some potential applications there, albeit we haven't done any subterranean work. We've just done the outdoor and some of the indoor as well. So what does this kind of thing look like? So this is a screenshot from system in terms of the data that we've collected. And this is just looking at occupancy. So it looks very similar to a point cloud, but actually all of these are voxels. And that's kind of useful. It's kind of what you'd expect to see. But what you can then start to do is to layer on the surface of the voxel the RGB value from the cameras. And that creates something which starts to look very realistic in comparison to what we're used to seeing. So in addition to that, the voxels have a number of other really nice properties as well. So really kind of moving beyond just points into something that's a bit more interesting. So firstly, they're 3D volumetric measurement units, which means it's very easy to calculate measurements of all of the objects, any of the features that are there. Secondly, as I mentioned, we can put layers on the surface of them, which currently we mainly use RGB, but we can use hyperspectral imagery as well. And there's lots of other types of data that you could start to layer on the sides of the voxels to make it interesting for analysis. So when we look at analysis, we can then start to apply, once we've got these layers on top and we've got the shape of these objects, we can then apply the AI and machine learning models to start to look at the semantic meaning of the voxels, basically to understand what they are. What does this voxel, what part of an object is it, essentially? And then we start to introduce this concept of the time, these time slices or this temporal data component. So each voxel can have an infinite number of temporal states. And this is really used for change detection. So as you start to do multiple passes of mapping, you can start to look at an object and you can start to see how that has changed over time. And importantly, you can start to get the machine learning to then look at the objects over time and to start detecting those changes. And I have some examples of that I can show you a little bit later as well. And lastly, this structure, because it has a permanent address, this creates a spatial database. And so the spatial database becomes very useful when you want to start querying and trying to find insight, intelligent search, bringing objects and even individual voxels back so you can start to analyze them. So all of that forms the basis really of the model that we're doing. So let me move on to digital twins. So what do we define as a digital twin? So Essentially, a digital twin is making a kind of a one-to-one virtual replica of the physical world, whether that's at the state level, city level, or even an entire country. All of those things are possible. So this is just an example of some of the data from a single pass that we've taken here in San Francisco. When you're building this model and using the voxel model and creating a digital twin, what you're actually doing is mapping everything that's visible. You're not just mapping one asset at a time. Anything that's above ground that you can see is being mapped and calculated as we go through. So this creates a platform which can provide a huge amount of intelligence and insight. If you initially might be interested just in one asset, but as you collect the data, you've collected all of the assets. So if you now want to go and analyze a different asset that you might be interested in a few months' time, you don't necessarily need to go out and recollect data. You just use the artificial intelligence to work on that model and extract all of the features and the assets that you want. And so it becomes very, very flexible for doing that and becomes very cost effective as well. And from this digital twin model, it's possible to then export the data out into pretty much any other format, whether that's a GIS platform or an asset management platform. We're very used to kind of exporting out into all of the known standards for this data. So it becomes a really useful tool. So how do we collect this data? So we have a mobile mapping platform which we've developed called SIMBO. This is an image of it. And it's pretty well equipped. So it has LiDAR, 360-degree cameras, a good quality IMU GPS, 4G, so it's a connected device, plus Wi-Fi, Ethernet, etc. And importantly, it's edge processing as well. This one device has NVIDIA graphics cards built into it and does all of the computation, all of the collection of the data in that box. It doesn't need to be plugged into a computer to do any of the processing. And all it needs is essentially power from the vehicle. So it's very easy to mount on pretty much any vehicle. It's very small in terms of the operation, which means one person can install it and really be ready to map in 5 minutes. As long as the frame is already on there, as long as you've got the mounts, you just attach the unit and off you go and you start mapping. It's also 5 to 10 times cheaper than any other mobile mapping solution on the market with LiDAR. And we really wanted to get to the point of reducing the cost for doing this kind of thing so that there'd be more adoption by cities, by utility companies of building these kind of models, making it more accessible rather than having crazily expensive hardware to do it. It's also really being designed to work with a non-technical person. So it's great if people have a lot of technical skills in GIS, that's always advantageous. But if you just want to get people that can operate an iPad, it's an iPad interface, and be able to drive, then we've designed a system that can do that. So in addition to the hardware, there's the software tools that come with it. And the starting point is what we call the mission planning. So we have a back-end infrastructure which can take a city, a state, or even an entire country, and to cut that up into daily mapping missions. And then those mapping missions are cut up again into what we call paths. So you can kind of see on the screenshot here, this is mapping. These are different mapping paths. And this is just designed to guide people who might not be familiar with mobile mapping to become more efficient with how they drive to make sure they're capturing all of the data. So you can plan all of the missions, just from a web interface. You can push them directly to the iPads ready for people to use and start driving. And we can even provide 10x10 navigation for the drive paths if the operators want to have that as well. The rest of the platform is really easy to use. Basically, you can see here that this is a kind of an overview of the system itself. If everything is green, that's all good. If we've got some red problems here, you can diagnose that as well. Very, very easy interface. It also has the nice ability to actually see, obviously, where you've mapped, but importantly, to see where the data starts to go bad. So if the quality of the GPS is poor in a particular area, or the IMU hasn't worked properly, you can see that in real time on the map. So rather than discover that in post-processing and then have to send somebody back to remap, you have the ability that the operator can turn around, recalibrate, and then carry on mapping as well. The other nice thing, because it is a connected device, that we offer support 24 hours. So not that many people map at night, but we have customers all over the world. So the idea here is that we can connect to the device and we can see what the problems are and resolve that remotely as well. So we have the ability to do lots of nice things there. So let me show you what this data looks like coming from the SIMBO device itself. So this is one single pass from the SIMBO, To start with, what we're just showing you here is kind of the raw voxel data. This is just the occupancy data. So it looks, again, very similar to kind of reflectivity points. But now you start to see the RGB values added onto the scene as well. And so very quickly, you're starting to create your digital twin. And it looks pretty realistic in comparison to what we're used to seeing in the physical world. Let me move on to the next slide. So now I want to talk about, for me, this is one of the most exciting bits, really how we use artificial intelligence on top of the digital twin and this model. And so we've developed a platform called VAMS, which is a fully automated platform using artificial intelligence and machine learning to recognize objects, but not just recognize them, to measure them and extract different attributes about the objects as well. So this is a screenshot from the system. These colors here are what the AI sees in the digital twin. So the AI is actually recognizing different objects here and assigning a different color to them as well. So as we input the data that we've collected into the model, the AI then works on all of this. So we've currently trained it to recognize about 50 objects. By the end of this year, we'll be up to 200 objects as well. But every time you see a box around something, this is the AI recognizing an object, but also performing a calculation as to the size of the object and also taking account to any other attributes as well. And it does this from the point of view of using the voxel data in the digital twin, but also the image data as well. So if there's information there, on signs, for example, then we can take that information off and we can understand what it is. So you have the ability within the tool to then look, it'll pop up and give you all of the information, around it. So you can see all of these different attributes which were fully autonomously generated, as well as seeing an image, of the asset as well. And you can automatically export that into, whatever format, be something like shape or NDS or JSON. You have that kind of flexibility in the system. So just showing you what that looks like in terms of the data that we've just been collecting. So we're going back to San Francisco. This is Embarcadero. So obviously this is the voxel model, the digital twin that's just been created. Now applying the artificial intelligence on top. So each one of these boxes is a different object that is being recognized automatically and having the calculation of the size and various other attributes taken from it as well. So you can see, and this is very fast. Even, for example, if it's not one of the objects that we've trained the system to recognize, as long as we can see, an example of the object that a human can recognize, we can train the system to recognize it very, very well. And we're talking in 98% accuracy once the system is fully trained. So it's very impressive. Here you see it as well, just working on a freeway, not just looking at things like the streetlights now, but looking at the lane model as well. So we've built those kind of features into the platform. Let me go across. One of the other nice things that we have is this concept of them being able to do a virtual survey as well. So, while all of the heavy lifting can be done by the machine learning, you have the ability to play around with the data as well and look at it. And this isn't just, a 2D static image. This is actually a 3D environment. So here somebody is, starting to look at the data, start to do their own measurements, just validate, some of the information that the machine learning has already kind of pulled out from it as well. And because this is in 3D, you're not just looking at a 2D object, you can rotate the object and see it from different angles. You can even change the view, as we see here. So understand what the computer is seeing, what the machine learning is seeing as well, and then pull up images and other attributes from it as well. So again, this becomes a very useful tool to cut down on the number of site visits that you have to make. You have this tremendous data set, which you can do a lot from the office just by using. So now talking about the fourth dimension, and this is a pretty interesting area as well. So as I said, the machine learning doesn't just work on the recognition of the object itself. It starts to look at how the object has changed over time. And this is just an example. So we have a pole here, which it's been mapped before, and then there's a new object that's appeared on the pole. And so it's recognized that as a change. Now, in this situation, it didn't recognize what it was. It didn't recognize that if it was a small cell or something else, but it came back with a recommendation of what it thought it was. So really, this is more of a kind of a decision support system. It helps humans make these kind of decisions. But as we start to train it more and more on the different kinds of objects that may well be installed and how things change, not only will it detect the changes, but it can classify those changes as well. And so this, for us, is a really exciting kind of model as well. Again, this all works with the first digital twin scan, and then as you do subsequent scans, in the future, you can start to analyze the change detection automatically as well. So the kind of applications that we see for this, I think around compliance, progress monitoring for installs, surveying. So we've had customers look at this from the point of view of 5G small cell installations, and whether installations are being put onto existing infrastructure, and do they fall within the parameters in terms of the size and where they should be as well. And so this was an automated way to check that that was being done, rather than going out and having to kind of manually survey as well. So kind of summarizing, a lot of this, what are the benefits really in doing it? So utilizing the voxel technology, looking at building a digital twin, leveraging the AI, the core thing it allows you to do is to map much faster than before. You're mapping everything very quickly, indeed. And you're also measuring as well. It's not just about mapping, it's also about calculating measurements as you go through. So intrinsically, that is there, as well as the additional attributes, all of the other features that normally you need to take down when you're doing a survey. By utilizing the SIMBO on a vehicle, you're replacing the need for larger field teams. Single person operation, one car can replace very large field teams. We've mapped San Francisco in a couple of weeks with just 3 vehicles going out and collecting the data. So it becomes very, very efficient to collect data, to scale, and even to start updating the data if you're having projects where assets might change over time. And again, you're mapping everything. This is really where you get a huge cost benefit here. You're not just mapping one asset, you're mapping everything that you can see in that environment, even if you don't necessarily need to use it at the moment. But if you do in the future, then you've got that data. And sometimes within government organizations, we've seen that different departments have different interests in the data as well. So sometimes building this digital twin becomes useful across that organization, across that kind of structure. So I just want to talk about a few real world examples of what we've done with this technology. We've got a lot, but I've just picked 3 just to give you an idea. So the first one was around traffic sign collection and mapping. So essentially, we built out the engine to recognize all signs in the US and the majority of the signs across Europe as well, mainly Western Europe, little parts of Eastern Europe as well. So utilizing the technology, doing all of the automated mapping, recognizing what the sign is, categorizing that, and then converting that automatically into XML that the client could then use and put into their mapping system. This project has mapped over 7 million signs already and brought that information back. Another really smart thing with this project is it has the ability to recognize signs that it's never seen before. So it can recognize something as a sign without necessarily categorizing it as to what type of sign. The reason that's important is it allows it then to come back. If you're moving, for example, into a new territory or a new country, it can come back and say, these are all the new signs that I've detected, where do they belong? And then a human can decide to add them into existing sign groups or to create new sign groups as well. So it's something that we call weekly supervised training. And so this just enables you to kind of scale up the system quicker than having to go through this initial process of training the AI and the machine learning, which can be very cumbersome sometimes in the beginning. So that's been a really interesting project for us. Another one was around installation compliance and change detection. So again, very much looking at 5G small cell infrastructure that was starting to be installed, and to look at whether we could detect the change in terms of equipment being added onto existing assets, but also importantly, was it compliant within the guidelines? So the size of it, where it should be placed, etc. And so this one has been, fascinating for us. It's still, we're still ongoing with this project as well, just doing it in one city to start with, and then looking to move it into other cities. But great potential for really looking at this change detection, automatic change detection. And then the last one for today is really looking around a mapping of roads. So this was a project that we did for a major automotive company. We mapped part of Los Angeles and Orange County to create a map for autonomous vehicles. And so, standard definition mapping, is fine for your mobile phone or, current navigation system in a car. But for an autonomous vehicle, you need to localize the vehicle within space. And so again, the data had to be high definition accuracy. So they define as 20 centimeters or less. For us, that's around 8 centimeters, so even more accurate. And what we were doing here was collecting all of the data from the environment, essentially making a model of the road network, the drive lines, as well as all the traffic signs that were being collected from it, as well as what we call localization objects. So these are the objects that the autonomous vehicle would look at to calculate its position using techniques like SLAM, for example. So really interesting projects as well, which we've delivered on, and we're now scaling that up to cover the majority of the US. So we have experience with doing, small collects for cities, all the way through to entire countries. In fact, last year we mapped Canada. So the vast majority of the road network in Canada, about 500,000 kilometers. And again, applying these technologies just allows you to do these larger projects much more efficiently than typically would be done before. So with that, that's the majority of what I have to say today. It would be great to answer any questions that you guys might have.
Thank you, Peter. So for a lot of us, it's from some of the questions, the first time we've heard much about voxels except through gaming. And the only reason I'm familiar with it is the volumetric filmmaking that's becoming popular, using that in filmmaking, especially for CGI. And a couple of questions here on that. Eric A asks, is each voxel assigned an RGB value for each face of the cube, or is the voxel one dominant RGB value in total?
It's good. So it kind of depends on the size of the voxels. So you can do both. Generally speaking here, we're just assigning an RGB for the voxel itself. But with larger voxels, you can then use different RGB values for it. The gain when you're really looking at 1 centimeter isn't that much by doing that, and increases some of the computation. So it kind of depends on the application, really.
Okay. Jeff has a question about your examples there, San Francisco or any other city. Is the training data for the extraction using machine learning specific to San Francisco, or do you have general training data sets for the feature extraction? Would it apply to San Francisco, Paris, Khartoum?
Sure. No, exactly. No, it's a great question. So it's a bit of both, in reality. So you have to, we're based in San Francisco, so this is obviously the place where we did the majority of the training, but we have taken this out into other cities. When we go into other cities, a lot of the infrastructure is automatically recognized, but sometimes there has to be additional, training, particularly if assets start to look different. That is magnified more if it's a different country. So you mentioned Paris, for example. So yes, infrastructure across in Europe looks very, very different to over here. And so there is a period of retraining. So we've done a lot of US training. Depending on the city, there might be a little bit more. And we've started to do some European training. So we've trained it for UK. We're just starting to look at Germany as well. Normally when we start to do sort of further afield, it's kind of led by client interest. So if a customer comes to us and they're very interested, then we start to customize the training and the algorithms for that particular territory.
Okay. Another question here. Rick M said, is there a standard for the idea of a voxel, in this type of application? Since you showed them at different sizes, are there IDs designed so that you know what a smaller voxel, how many smaller voxels fit inside a larger voxel?
Absolutely, there is. So actually the addressing system, which I won't get into because it gets very complicated, and probably actually my CTO is better at describing this than I am, but they relate to each other. So the addressing is built up in terms of the relations from megavoxels to smaller voxels as well. So it is possible to understand where these voxels come from. There's relations within that.
Okay, so another question here. This is an obvious question. Anytime we're looking at a new type of solution or new to us, someone asked, is there any major cost saving use, a voxel approach? I'm sure you've looked at this and your investors. Is there a cost saving to the end user of using this approach compared to certain others?
Yes, primarily because you're essentially creating a spatial database of all of the information which you can always access. This isn't a case of taking a bunch of LAS files, putting it into some kind of viewer and then using some tools to extract intelligence. You're creating a model which always exists. Think of it as a computer game of your city. And then on that model, which is always live, you're applying the artificial intelligence. So that's why that model can always be current in terms of extracting additional assets, in the future. And that can either be the assets that we've trained the system to recognize, or it can be custom assets. So very often, companies will come to us or cities and they'll come back with a different asset that we haven't seen before. And so then we go through a period of training. Typically it can take from 2 weeks to a couple of months, depending on the complexity. And we train the system, and then we deploy it on the existing model. We're not going out and having to do another collection. It just starts to work across that model and extract all of that data for you. Okay, all from the comfort of your home.
Yeah, if I read into that, perhaps it's that the cost savings is that you don't have to process it into something else or several of something else to be able to do different extractions. You're saying it's creating the model right away, yep. And you just apply your AI directly to that. Was that?
Absolutely. Another thing to point out, and again, this is more of a technical point, but the AI that we're talking about here isn't just semantic segmentation on 2D imagery, which a lot of people try and use. What we're doing here is we're doing semantic segmentation on the voxels themselves. So it's a full 3D model. So when we're doing the recognition, the AI isn't just looking at this flat 2D image and trying to decide which pixel goes where and what it's made from. It's really looking at all of the objects in 3D, which gives us this very, very high recognition rate.
Okay. Lego blocks, patterns of Lego blocks,
exactly.
Blocks in 3D. Sorry, I shouldn't have said that.
It pretty much is that.
You probably get tired of hearing that.
A few times.
So Kirk asked, this is one I wanted to ask as well. Did you research exclusively photogrammetric approach to building your models? Is there a way to use LiDAR or mixed? Because there's certain advantages to mixed. They can recognize things in different conditions that others can't. So.
Absolutely. So the interesting thing with the voxel model is this multi-resolutional capability. So we don't always have to use 1 centimeter or 4 centimeter voxels. We can use bigger voxels. And that means that if we can start to generate point clouds in different methods, we can use that data. Now, for the kind of work that we do, LiDAR is just the most efficient way to get high resolution points, which we can convert into the voxel model. And we can take that data both from terrestrial mobile scanners or aerial LiDAR as well and ingest it. We have looked at taking data in from different sensors, things like stereo cameras, for example. And we've even looked at radar and using, you'll have much bigger voxels, but you can actually create a map using radar as well. So there's different ways that we can have different types of data stored within the voxel model. Whether you can get the same resolution as LiDAR, I'm not sure you'd always be able to with the current solutions, but the model's kind of future-proof. So, the input method is almost, secondary to the model itself.
Okay, I'm thinking of applications where, because of a certain precision requirement, somebody's doing a really high-end mobile mapping system, and but that data is not wasted. You could turn it into something. Into Absolutely. A voxelized format, right?
Yeah. So this happens a lot, actually. So customers do come to us with data they've collected on other systems, such as Leica or Trimble, and we can absolutely take that data and convert it into the voxel model as well. There's kind of a trade-off, between sort of great solutions and systems that are out there, but very, very high cost. And so when you have that kind of environment, sometimes people aren't going to roll it out in the same way and really kind of create this concept of a digital twin. So the point of our hardware was really to just try and reduce the cost and just get more of it, out there that people can be using, but not exclusively to the detriment of, data that they've already collected, which we could use and model within the voxel map.
Oh, okay. Yeah, well, Marion B asked a similar line of that question, but about aerial LiDAR data. So that's, as you Absolutely. Said, that's. Okay, cool.
Yeah, and so we're actually working as well, actually with Ron here from Geo1. So, Ron will tell you more about his business, but one of the things that he does is capture very high quality, aerial data from helicopters. And so, there are some projects where we're taking the aerial LiDAR data from Ron and imagery as well, and then merging that into the voxel model with the ground-based collection that we've done. And that kind of, completes the whole model. If the city really wants to see, all of the buildings, right to the top of them, the roofs and everything else, then obviously you do need that aerial component.
Oh, okay. Yeah, we heard a lot about mixed yesterday. A question from Chris R., a surveyor. Does the software recognize and highlight changes between data sets in the same areas of interest, but captured days, weeks, months, years apart? I think you covered that, but.
Yeah, it can too. So when we're doing change detection over time, that's still at the moment custom implementation. So we have that working, but it's not as if it kind of is a drop-down menu and you can just select anything. So
Okay.
it kind of depends on the data and the kind of changes that you want to determine. But absolutely, we can do that from multiple data sets. The other thing is within the metadata for each voxel, there's attribution. And so we actually know where the data was generated initially in each of those time slices of the voxel from which data set. So we can really kind of delve, in quite a detailed way into all of those things.
Cool. Okay, and we have time for one more question here. This is about the SIMBO, and I must have missed it. Is the SIMBO, is that an acronym for something?
Yeah, but it's symbiotic. So eventually the idea, we're actually working on a 3rd generation device, which we hope to be ready next year. And this will actually be even smaller and at a much lower price point. And we imagine that we'll be able to install these onto existing fleet vehicles. So for example, if cities have public work vehicles, they might want to attach some of these sensors on. So as they're doing their kind of regular job, they're passively collecting this information, which can be built into it. So then that kind of symbiotic relationship is kind of where SIMBO came from as well.
Oh, okay. Well, Lyle's question talked about, the Velodyne puck that's up underneath,
Mm-hmm.
Is it, how's it removing the obstructions to that? Do you have that windowed off?
So when you say removing the obstructions, you mean how it's mounted, or you mean kind of cars in the way, people in the way, etc.?
Yeah, or actually the device itself, the way it's mounted up under there, it's going to have like a fan,
Yeah, you don't really see that effect. So that's one of the interesting things with LiDAR. So if you have pretty thin poles close to the device, you don't get a lot of missing information, because as you're driving through, you're kind of filling in that gap. It's not just one pass. It's generating millions of pulses a second. So you see that issue. Obviously with cameras, that would be a bigger issue, which is why you have them mounted at the top. The other thing just to mention on that is the LiDAR is actually detachable from the unit. So you can choose different types of LiDAR. So we support the Velodynes, and we also support things like the Ouster LiDARs. And we have a kind of an upgraded version of the SIMBO I showed you, which has 2 LiDAR sensors, which just gives you more vertical resolution, if you want to, scan higher.
Oh, okay. Okay. And then with most mobile mapping systems, you've got like a positioning unit, IMU, GNSS. Yep. And do you like post-process PPK or something like that after the fact?
Yeah, generally speaking, in our current workflow, it's mainly PPK processing, or PPP. Okay. We use the Novotel IMU inside it as well. So we're getting multi-constellation plus IMU corrections, 200 hertz. So there's a lot of, to get down to the accuracy level in terms of absolute accuracy, there's a few different techniques, obviously, that are employed to generate that data.
Oh, okay. So it's like a Novotel span type.
Exactly that. Yeah.
Okay, cool. All right, we're going to have to wrap up. Sorry, you lost a couple of minutes at the beginning.
No problem.
There's probably going to be other questions come up. Again, if you have more questions for Peter, you can go into the guide and book a Zoom meeting through a calendar and there, clicking on that. So we're going to move on to the next session.
Thank you very much.